and I was going to go into an example. So we can think of an example here as the level of cholesterol in the serum. Let us assume that it is normally distributed. Normally distributed means it's this nice bell-shaped curve, all right? Most of the observations are in the middle, but some people have got very low levels and some people got very high levels. The mean is 211 milligrams per 100 mils, and the standard deviation is 46, and this is in a given population. And I'm using population parameters here, mu and sigma, because I'm assuming these are for those populations. Hello? Someone want to ask a question? Okay. What's the...
can try to mute everyone.
Yeah, obligatory mute I think would be good. Let's quit from here. So, okay.
Perfect. So everyone's muted.
That's everyone. Okay. Sure. Oh, I'm back. So, right. Okay. So we did this already yesterday, and we were talking about the population parameters, the mean and the standard deviation. The standard deviation is the variability around the mean. So if this is a large value, 46, if this was large, let's say it was 100, that means there's a lot of scatter. If it was small, like let's say 10 milligrams per 100 mil, then it would be a narrow distribution. Okay, so we can, with this distribution, we can work out the probability that a randomly chosen individual has a serum cholesterol level greater or equal to 245 milligrams per 100 mils. So we can work this probability out. So 245 is here on the distribution. It's 31 above, 31? Yeah, 31 above the mean here, 211. So we want to know what this area is, and this area will give us the probability. Okay, so we want to know that. That's question mark. So the normal distribution, the whole area under the curve is 1. So all the observations, or the whole population, if you like, lies under this curve. We can estimate the probability in question by determining the proportion under the curve. Okay, so the area that lies to the right of the point that we have specified, 245. Okay, so the textbook gives table of areas for the normal curve, such as this one, which comes from the Pagano and Gavreau book. And of course I'm biased, so I prefer this one from my book. I think it's a little bit clearer. So we can use this. They're both basically the same. What we need to do is to work out Z for these tables. So if you look back at this table, this column here is Z, okay? And the second decimal place is given along at the top. And then the body of the table gives the area and hence the probability, okay? So it's pretty straightforward. We have a Z value indicated by the left-hand column. Second place is along the top, but the numbers in the body of the table are actually areas, and they're the areas to the right side of the distribution, okay? So for example, if we have a Z of 0, that means we're 0 standard deviations away from the mean. that gives us 0.5. You see this number up here, 0.5. Of course, half of the distribution is above. Actually, half of the distribution is also below. And as our Z value increases, you'll see that this proportion gets smaller and smaller. And once we get to 2.9 or 3 standard deviations away from the mean, you can see this area in the tail now becomes very small, 0.0019, for example. Okay, so we need to work out Z, which is that left-hand column in the previous table. And we do that by using this simple formula, which tells us how far away the value that we're interested in is from the mean in terms of standard deviations. Okay, and this gives us the standardized normal distribution. So, okay, let's do the calculation. It's the particular value here, take away mu, our specified mean. The population mean was 211, and the standard deviation, population standard deviation, which was 46. So we put the numbers in here, and that gives us a Z value, all right? Okay. So we then use this number to look up in the table, and it goes 0.739. Okay, we can only go to 2 decimal places, so it's 0.74, all right? So 0.7 here, see this arrow, and 0.74 at the top. That gives us this value here in the table. Okay, so this corresponds to 0.74. So what is that number? It's 0.2296, okay? Near enough 0.23. Okay, so the nearest value is 0.74, and that gives us a probability of 0.23. Okay. So therefore the probability that a randomly chosen individual from this population has got an SCL above 245, equal to or above, will be 0.23. What's that as a percentage? The whole area is 100%. This is 0.23. Let's say it was 0.5, that's 50%, right? So what would this be? 23%, right. Okay, so it's quite easy. We just multiply by 100 and we get a percentage, okay? So what about 0.05? What would that be? 0.05, 0.05 in terms of a percentage, just be 5%, right? Okay. All right, so this is the standard normal distribution. What we've done is to convert our numbers, the mean and the standard deviation, using those population parameters, we've turned it into a standard normal distribution. This means, because we're dividing by the standard deviation, that means that the distribution has got a standard deviation of 1 and a mean of 0, okay? Because we're looking at differences from a specified mean. So this is the standard normal distribution. Okay, so it's got a standard deviation of 1. What would the variance be then? I think everyone else is muted, so it's only you guys. What is the variance again? What's the relationship between standard deviation and variance? The root, okay. Which is the root of which?
The standard deviation is the root.
Okay, so if we got a standard deviation of 1 and we square it, that'll give us the variance, right? Okay, so what does that make the standard, what does that make the variance? It's 1. Okay, so it's quite nice. We've got standard deviation and variance of 1. Okay, so the standard normal distribution, the tables that I've been showing you, whether it's in Pagano or Pagano and Cover or my book, it's the tail of the distribution that's given as an area. Now, it's given as the right-hand tail, and it only gives positive Z values, but of course there are negative Z values if you go below the mean, all right? But there's no point, because it's a symmetrical distribution, there's no point in duplicating basically the same table for negative values, all right? So you've got a negative value, then you're looking at the bottom part of the distribution.
it's skewed to me.
If it's skewed, then it's not a normal distribution. So it's a bit more problematic. It becomes more approximate. Sure. We need to make an assumption here that it is a normal distribution. It's a good question. Thank you. So for a particular value of Z, in the table, it's the area, as I've said, and for these tables, it's to the right of the value that you're interested in. Okay, so it's the right-hand tail. Now this is slightly confusing because when we do the formulas, we'll do it in Jamovi, it actually looks at the left-hand tail, just to make it difficult for you. But anyway, you will manage, don't worry.
So 245, we see what's the right.
To the right, yes, in the table, to the right, yes. Okay, so let's just look at some particular values. So Z of 0, I already showed you, the area to the right is 0.5, half of the, it's 50%, right? Very easy. What about 1.64 standard deviations? So Z of 1.64, well, that corresponds to 0.05 in the right-hand tail. And in percentage, remember, 5%, okay? What about nearly 2, 1.96? Well, this number actually corresponds to 0.025, okay? So 2.5% in the tail. Okay, so probability that a particular Z selecting at random would be greater than 1.96 is equal to 0.025, right? That's the probability. Okay, so standard normal distribution, it's the relationship between X and Z, and this is the formula which I've shown you. It's pretty straightforward. Basically, it is standardizing the difference between a chosen value and a population mean. Okay, so the Z here that we calculate, it represents the distance in terms of standard deviations. Okay. So the standard normal distribution is symmetrical around 0, and the area of the curve, area under the curve to the right is equal to the area of the curve to the left. Okay, so as I say, it's symmetrical. So what about the area between -1 and +1 standard deviations, or Z is equal to -1 and +1? So what we're talking about is, so we look up what 1 is, 1.0, okay, and 1.0 here, that's this, 0.1587, okay, that's nearly 16%. Okay, so we get 0.159, all right, and because of symmetry, as I say, -1, the area to the left will be 0.159 as well, okay? So when we're looking at +1, Z is equal to 1, to the right of that point, we're going to have 0.159. And if we've got -1, Z of -1, although we don't have it in the table, because the distribution is nice and symmetrical, the area to the left represents